Okay, hey everybody. We're going to go over 12.4, which is Bayes' rule. This is, again, having to do with probability. Most of the sections are basically just about different probability rules. Bayes' rule is usually dependent on the state of the world. So this is different than the probability we were looking at before. It's not just looking at experiments. We're also trying to this would be for something we have like outcomes for already. Maybe we already have data for it. So for example, I put in here, we might need to predict whether or not someone has coronavirus. We would need to know if these two states of the world, so we have S1 and S2, and the first one, someone has corona, second, someone does not. So those are basically just the two states of the world in our experiment. And collectively exhausted it refers to all these states of the world, and it's just all of the possibilities. And then prior probability would be a probability assigned to the state of the world. So we often, we may already know an outcome to a situation or already have tested it, but maybe we're testing for a different outcome this time because we would like to obtain more information. A likelihood, it's kind of hard to describe, but it's not just a probability. It's for each possible outcome, there's a likelihood given that state of the world. That'll become more clear in the example. Posterior probability is basically the resultant of Bayes' rule. So when we actually go through and do Bayes' rule, we get a posterior probability out of it. So like it says here, it's post-experimental. And we basically just combine prior probability, so like prior data, and the likelihood of these occurring in the experiment. And we will need, if you look below, in order to have Bayes' rule, we need our two conditional probability statements from above. And since the states of the world are collectively exhausted, one of our experimental outcomes, O of J, will need to occur with one of the states of the world. So that's basically the condition with Bayes' rule. It's like we have to have one of the outcomes occur within one of the states of the world. We also will use one of the probability statements from a couple sections before. These are, here, this has a parenthesis missing. But these are what we would refer to as joint probabilities because they are two things joined together, versus when I just have something by itself, that is a marginal probability. So if we substitute our second equation and our third, or substitute the second into the third, we basically get the summation of all of the outcomes given the state of the world multiplied by the state of the world. And this is going to tell us the probability of O sub j, or whatever outcome that would be. J normally would be a number depending on what event we're looking at. So then if we substitute some more, we eventually get Bayes' rule. So this is the final kind of formula we would use to solve any problem with Bayes' rule. It's basically just a more advanced version of conditional probability. So this example will make the states of the world and posterior probability and Bayes' rule kind of all come together. So suppose that 1% of all children have tuberculosis, or TB is what we'll refer to it as. When a child who has TB is given a Mantoux test, a positive test result occurs 95% of the time. So a lot of times, like I said above, we are dealing with stuff that we already have data for and already have tested, and we're usually taking this and trying to predict something else. So when a child who does not have TB is given the Mantoux test, a positive test result occurs 1% of the time. So that might just be like an error. That's probably like the margin of error with the test, is that sometimes, 1% of the time, one out of every like a million kids gets a false positive. So we want to know, given that a child is tested, so given is kind of that hint that we're going to be doing conditional probability with Bayes' rule. And so given that a child is tested and a positive test result occurs, what is the probability that the child has TB? So we want to know, okay, given that, knowing that we have this false positive probability, what is the outcome if we test a child and the positive occurs? Is it really positive or is it a false positive? So for the solution, we have to first define the two states of the world. So the child has TB or it just either does not. And the possible experimental outcomes. So again, we have to have, for every state of the world, there has to be some sort of outcome. And so it's either positive or non-positive. And they did tell us in the problem above that there was a 1% chance that a child has TB and a 99% chance it doesn't have TB if it's tested and positive. And the likelihoods of a child being tested for TB and having it is 95%, like they told us up here. And also they told us that we get a false positive 1% of the time. And then, for here, this would be saying if you have a child who has TB, they would get a non-positive result 5% of the time, which it tracks in line with the first O1 given S1. And then 99%, that's just the opposite of our 0.1. So we are actually looking for, they told us above, what is the probability that if a child is tested and gets a positive result, do they have TB? So that's why we're doing S1 given O1. So we basically just take Bayes' rule above and we plug in, well, first of all, I and J is going to change to what we are looking for, which is P of S1 given O1. And we will plug in our values, which gave us 0.49. So there's a 0.49 chance that if we test a kid and they have TB, that they would get a non-positive test result. So we'll actually do a separate problem now together. So I'm going to go ahead and read this. A desk contains 3 drawers. Drawer 1 contains 2 gold coins. Drawer 2 contains 1 gold coin and 1 silver coin. Drawer 3 contains 2 silver coins. I randomly choose a drawer and then randomly choose a coin. So we have 2 choices, basically, which are 2 events. If a silver coin is chosen, what is the probability that I chose drawer 3? So more than 1 drawer contains a silver coin. So let's say if I have a silver coin, what was the probability that I chose one of those 2 drawers? Because the first drawer doesn't even have a silver coin in it. So the first thing that we always want to do in probability problems is let's define our events. So D1, D2, D3, this will be that drawer 1 chosen. And I'm just going to save us time and duplicate this a few times and just change the number. Okay, so we either choose drawer 1, 2, or 3, and then our other event, I will call S, is the silver coin is chosen. So now, since we have 3 choices for choosing a drawer, we need to have our prior probabilities, because if you guys remember in the previous solution or example, they gave us like those probabilities ahead of time. About 95% of children test for TB. So we kind of have to make up our own or intuitively think about it. But since we have equal chance of getting every drawer, they're all going to have probability. They're all going to have the same exact probability because you have an equal chance of like choosing each drawer. It says that we randomly choose one. So that would mean that the probability of D1 and D2 is equal to D3. And that would mean that they all have the probability of 1/3 because they all need to equal 1 if we added them all together. So let's remember, we only care about silver coins. So let's talk about only the drawers with silver coins. We know drawer 1 has no silver coins. So I'm just going to say no silver. We know that drawer 2 has 1 silver coin. And we know that drawer 3 has 2 silver coins. So kind of right off the bat, you have to know that if we did choose a silver coin, we probably did not choose drawer 1. So let's go over the likelihoods, which are those joint probabilities. So first off, we have to do it for every single one. If I chose a silver coin, given that I choose drawer 1, what's the probability of that happening? Well, drawer 1 doesn't have any silver coins, so there is a 0% chance that you would have even chose that. So then for D2, well, there is 1 silver coin in there out of 2. So probability of that happening is 1/2, or likelihood of it happening. For drawer 3, there are 2 silver coins in there out of 2, which is 1. So I think sometimes people get confused. Remember, these are just the likelihoods of this occurring based on what we already know is in the drawers. So this is not the probability. If you notice, the denominator is 2 because there is in total 2 coins. So by Bayes' rule, let's all write that out. So if I look above, Bayes' rule always is P of S of I given O of J. In our case, our S is our state of the world would be the drawers. So P of, and we are looking for D3 because that is the drawer with the most silver coins, given S, which equals P of S given D3 times P of D3 all over P of S given D1 times P of D1 plus the same thing, just changing the drawer. Sorry about my handwriting, trying to make sure this video is not too long for you guys to watch. Plus P of D3, okay. So now that we have this all written out, we basically just have to plug in the values. Oh my God, I'm so sorry. Put my hand down on the screen. So basically, P of S given D3 times D3. Well, if we look above, we know that's 1/3 up here because P of S of D3 is 1. 1 times 1/3 is just 1/3 in the top. All over P of S D1 times P of D1. So 1/3 times 0 in the bottom because there is a 0% chance of us choosing drawer 1. Plus, well, we had a 1/2 chance of choosing drawer 2, or likelihood of it happening. And then 1 times 1/3 like we had above. So this would give me, okay, let's see, we'd have 1/3 in the top plus 1/6 plus 1/3, or if we change that into 6, is 2/6. So 1/3 over the 3/6 would be 1/2. So that would give us 1/3 times 2/1, which gives me 2/3. So the answer would be 2/3. So the probability that I choose drawer 3, given that I already had chosen a silver coin, is 2 out of 3. So pretty good. So that one's not, so Bayes' rule is not too bad, just basically plugging and chugging the numbers. Thank you guys. Keep watching for the next section.